Hello, everyone, and welcome back. We are starting Chapter 7, which a big part of Chapter 7 is what's going to be called related, it should be a D, related rates. We're going to be doing this for several days now. And this is just an introduction where we're going to talk about notation and making sure you're familiar with that. Now, what we've done in the past is we've always looked at things like dy, dx. That's the notation for derivatives. And if you remember, the D comes from delta, and by remember, I guess this is only to those who I mentioned this to, where delta means change. So what's talking about is we always talk about dy dx as the change in y with respect to the change in x. As x changes by just a little bit, an infinitesimally small amount as x changes, how is y changing? For example, if you had a function y equals x squared, dy dx by our power rule we know is 2x. Well, what's that saying is that if you have a function y equals x squared, it looks something like this. Well, it's saying that the rate at which this function is changing, the rate at which the y values are changing, so notice at 1, you're at 1 here, at 2, that should technically be 4. I didn't draw it too well. It's a very poorly drawn graph, I apologize. Just make it a little note, drawn poorly. But the rate at which it's changing, well, I guess that should be 1. That's actually the truth there. So that should be 1 based off how I drew it, and that's 2. The rate at which it's changing, so it's at 1, and then it goes up to 4. It's changing by a linear rate. The y values are. So every time as x changes by just a little bit, as you went on to like 1.1, well, it's gonna whatever it's at would, times by 2 in a way. And then as you keep going, 1.3, as you increase x by just a little bit, I know you can't see that, 1.3, the y value again would be increasing by a rate of 2x. So this was always talking about how y was changing with respect to, infinitesimally question mark, I don't know how to spell that. How y is changing with respect to infinitesimally small changes in x. And that's what we've been doing with derivatives. Okay. And I just want to make sure you understand that notation, that dy dx. Okay. Now related rates are going to be talking about that, derivatives and rates of change, but with respect to more applications of it. So let's look at a anatomy example. Here we go. So I'm going to define a few variables, and then we'll practice this, and hopefully it clicks too. Okay. So let's define, and I have this down. H is going to represent a height. E will represent your eye size. Let's do A represents your age, and then I'm going to do C represents the love of coffee, like so. Okay. So if you saw DH, DA, well, what is that saying? That's saying the rate at which height is changing with respect to age. So visually, what would that look like? Is you have age and you would have height. And the idea is like as you get older, as age increases by just a small amount, well, what's happening to your height? How is it changing? Well, if you think about this, as you get older, as your age gets older, your height, well, you are increasing. And you increase pretty quick in your young years, and then you start to slow down as you become a teenager and you become an adult, and then you stay relatively the same height for a long time. And then you will start to shrink as you get a little bit older, as your bones compress. That's the right word. Compression. Yeah, I think it's compress, not contract. So you can see that DHDA would look something like that, where DHDA is both positive and negative at different times. Okay. What about another one? Let's say, what if we looked at DEDA? So what's that saying in relation to my anatomy example? Is that's the rate at which your eye size changes, your eye size is changing as your age changes. Okay. So again, graphically, you can say, okay, age, my eye size. And maybe you don't know this, but as you get older, your eye size actually does not change. It stays the same. I believe that the eye size of a baby will now be the same eye size their entire lives. So DEDA is a constant rate here. Constant rate. Okay. Let's do two more. Let's see, what can I come up with? What about, what if we do DH, your height? How is height changing relative to your love of coffee? And maybe you don't have a love of coffee, and that's okay. So that means the rate at which your height changes, with respect, I'm not just using the math language, more to how your love of coffee changes. Okay. So visually again, we're saying the love of coffee. And as this increases, or as it makes a small, infinitesimally small change, what's happening to your height? Well, if you like coffee more, the more coffee you like, believe it or not, your height, according to studies, when you're a teenager, will actually start to decrease, but not much. I mean, if you drink coffee as a kid, you're not going to, lose out on a foot of growth spurt. Per se, a lot of that's still genetics, but if you do drink coffee, they say it stunts your growth a little bit. So your height might decrease before you get old enough where, coffee's not really going to affect your height anymore, which that will stay zero. Your height will stay the same regardless of how much you like coffee. So you can see that might be something like that. Okay. And then what about DCDA? That would be the rate at which your coffee love is changing as your age changes. So as age changes by just a little bit, what happens to coffee? And this is all relative to the person speaking. I don't think we can make too many assumptions here, but if it were me, as I got older, I didn't like coffee. I had zero interest in coffee, my rate. And then as I don't know what happened to my taste buds, but all of a sudden that bitter taste with a little bit of milk added to it started to increase. And as I got older, the rate at which I like coffee increased. And then I guess as I've gotten older, I still enjoy it. I still enjoy coffee, and I'll have a slight positive rate. It's still increasing. I still enjoy a good cup of coffee. Okay. So that's the idea, but it's really about understanding notation in this lesson. And I just want you to think about that. So again, the derivative is about how something is changing with infinitesimally small changes, like an exact moment in time. So as age changes by just a little bit, how is coffee changing? And that's what we'd be studying. Okay. Hope that makes sense, and I hope the lesson goes all right for you. If you need any help, reach out to me. All right. Bye-bye.